obviously when you lecture record stuff, it creates a scenario where people can not breathe -16 to come in or whatever. All right, so I apologize for the kind of hiatus. It wasn't the plan. As one of the associate deans in the faculty, I had a meeting that I had to attend that has implications on construction-related matters in the faculty, and so the meeting went well. We ended up getting a $2-point-some-odd million project funded, so which is good. It's not for this building. This room is next. We're hoping to get this room renovated in the next couple of years, so that's another project that I'm working on. But nevertheless, I couldn't miss the meeting on Tuesday, so I had to. That's why we fit in the acid-based one. But they're not so disconnected that it hopefully results in a major deviation of the course of trajectory of the pulmonary stuff. So we talked a little bit in the past about some respiratory mechanics, how we breathe, why we breathe, aspects related to alveolar ventilation, minute ventilation, the fact that they're really never going to be the same. Minute ventilation is the amount of air we move into and out of the body. Alveolar ventilation is the amount of air that we deliver to the lungs to participate in gas exchange. Alveolar ventilation is heavily dependent on breathing pattern, as we showed. So if you're basically at a given minute ventilation, if you breathe deep and slow versus fast and shallow, deep and slow results in a better matching of minute ventilation to alveolar ventilation, because you basically don't ventilate just the physiologic dead space. You push more fresh gas into the lungs. So we talked about we have to have basically a breathing strategy during exercise that allows us to minimize breathing at near total lung capacity. We also don't want to breathe near residual volume, where there's high elastic work of breathing and resistive work of breathing. And we also want to maintain our breathing pattern such that we try to expand tidal volume primarily and minimize the extent to which we increase breathing frequency. So we have a lot of things that are going on to optimize gas exchange efficiency, alveolar ventilation, minimize the work and the oxygen cost of breathing, and try to eliminate the respiratory system as a potential competitor for oxygen delivery to the peripheral tissues. Okay, so it's kind of the context. So in this lecture, we're going to talk a little bit about, start off talking about the ventilatory breathing pattern and operating lung volume responses to exercise. So this is a busy graph, but it's going to animate in. The reason I post both PowerPoint, or I guess Charlotte and I post both PowerPoint and PDF, is that my expectation is that sometimes I'll animate things in a particular manner. So I think many of you probably study from the PDFs, but if it were me, I'd study from the PowerPoints, because then the things come in a manner that, at least for me, I would want it taught to me to try to understand it. So if you look at a slide in PDF and you're like, holy shit, this is overwhelming, Jensen smashes so much stuff into there, which I do, and it's always a yin and a yang. Some people like it, some people don't. But the idea is that you can always break it down visually into smaller components if you go back to the actual PowerPoint slide and see them animate in. So hopefully it's not as overwhelming when you see all these lines. Where do I start? What does it all mean? But if you go back to the PowerPoint, and just as you're prepping to study for final exams and stuff, the animations can help in that regard to maybe decrease how overwhelming some of the content is. So here what I'm showing you are a series of plots, everything plotted against exercise-induced increases in VO2 as a measure of exercise intensity, or the rate of oxygen consumption. So first, if you look at the ventilation response, so minute ventilation, so the product of tidal volume and breathing frequency. This is not alveolar ventilation, minute ventilation. You can see that ventilation rises pretty linearly with increasing VO2, and at a point, usually somewhere around 50% of your peak exercise capacity, you get this deviation or this acceleration in ventilation that's disproportionately greater than the rate of oxygen consumption, and we'll explain why that is. But that's basically ventilatory, respiratory compensation for metabolic acidosis. Remember, clearing out carbon dioxide from the body is a very rapid way that the respiratory system can try to minimize disturbances in acid-base balance. Basically clearing out carbon dioxide from the system, which serves to decrease hydrogen ion or increase pH. So it can cause an alkalosis in the setting of an exercise-induced acidosis. Okay? This increase in ventilation is achieved primarily, so basically where the axis is labeled, you can see here this is tidal volume in liters, and this is going to be breathing frequency in breaths a minute, okay? And the colors and the labels correspond obviously to the things in the graph that they're referring to. So you can see the tidal volume expands pretty linearly early in exercise, and then at a point it plateaus. Somebody asked the question earlier, well, does tidal volume just keep plateauing? Do we take these vital capacity breaths? No, it's not really a good advantage to take the biggest breath that you can possibly take every single time, because again, every breath out will be forced to breathe near residual volume where the airways are collapsed and resistance is high. And every big breath in will force you to breathe against the elastic recoil of the lung and the stiff rib cage. So we have this optimization of breathing pattern, which seems to be some type of competition between optimizing gas exchange early in exercise by expanding tidal volume, but then increasing breathing frequency later on once tidal volume expands to about 60% of vital capacity. And you'll see why this occurs. This occurs in large part to keep tidal volume expansion on that linear portion of the respiratory system sigmoid pressure volume curve, where we know that the compliance is high and where the work of breathing is going to be minimized. Where the work of breathing, again, is how much pressure the respiratory muscles need to generate to move a given amount of air into and out of the lungs. Okay, so again, we want to stay on that linear portion of that S-shaped curve. We want to avoid the high end and the low end. So breathing, our tidal volume expanding to about 60 to 70% of that generally will satisfy that criteria. That's reliant also on the behavior of operating lung volumes, so end expiratory and end inspiratory lung volume, which I'll show you later. Now, for ventilation to keep increasing in the setting of a plateau of tidal volume, what has to go up? If ventilation keeps rising, and ventilation is the product of tidal volume and breathing frequency, and tidal volume plateaus, what must be happening to breathing frequency during heavier intensity exercise? So it surges. So you do get rises in breathing frequency with increasing exercise intensity, but it surges quite dramatically, what we call a tachypnic surge, near the end of exercise to compensate for this plateauing of tidal volume expansion. So we increase the rate of breathing to compensate for the plateau in the volume of each breath to support the increasing demands for ventilation. Alveolar ventilation, as you would expect, because we have a fixed physiologic dead space, so those the anatomical dead space, and we do have obviously some physiologic dead space, relatively negligible in healthy adults, is, as we showed last time, is that depending on the breathing pattern, the minute ventilation and alveolar ventilation are not identical, right? They're not, inherently a 5 liter a minute ventilation might be, depending on breathing pattern, a 4.5 liter per minute alveolar ventilation. And I don't know how well represented this is, but you would expect that perhaps at the end of exercise, because of this change in breathing pattern, which would facilitate basically a greater disparity between minute ventilation and alveolar ventilation, the difference between minute ventilation and alveolar ventilation might widen. But the general idea is that both minute ventilation and alveolar ventilation increase in proportion to exercise intensity, and during heavy intensity exercise, they increase disproportionately more than the rate of oxygen consumption. Okay? In terms of the alveolar partial pressure of oxygen, so this is the alveolar PO2. So basically, again, in the conservation of mass model and the mass and heat flow models, this is that high energy component of oxygen delivery from the lungs into the blood. Okay, so it's basically the driving pressure pushing oxygen from the lungs into the blood. And so you can see that it remains relatively matched, which means that the rate of oxygen delivery into the lung from alveolar ventilation is about the same as is being removed by metabolism. Right, so that's how you ultimately, again, inflow is equal to outflow, and so in this case, the alveolar PO2 is relatively constant. But when you have this disproportionate increase in ventilation, where you're bringing, if you think of it this way, ventilation is now increasing disproportionately more than the rate of oxygen consumption. So you're bringing more oxygen into the body than is being consumed by metabolism. And under those circumstances, you would have, in this case, inflow is greater than outflow. So the net effect is that you would actually have this exercise intensity dependent rise in the partial pressure of oxygen in the lung, which would then widen the pressure gradient for oxygen, diffusive oxygen flux from the lung to the blood to support that demand, because now the blood that's coming back to the lung, the mixed venous blood, is very desaturated. So whatever you can do to widen that alveolar to, or that venous pressure gradient will facilitate oxygen exchange and try to maintain oxygenation of the arterial blood. If you look then at the alveolar and arterial CO2 levels, remember CO2 is such a soluble gas that generally the amount of carbon dioxide that's in the blood and the lung are relatively similar because they can achieve equilibrium very, very quickly because CO2 is, what did I say, 25 times more soluble than oxygen. And so it moves along a very relatively small pressure gradient to achieve almost complete equilibration. And so during heavy intensity exercise, where ventilation begins to increase disproportionately more than metabolism, you can see that we actually get a blowing off of CO2. And this has beneficial effects in terms of the regulation of acid-base balance during exercise. In terms of the arterial PO2 levels, you can see that actually in most healthy individuals, they remain relatively constant. So we really don't have much in the way of arterial blood oxygen desaturation during exercise. Our respiratory system is able to accommodate these dramatic increases in metabolic demands without blood oxygen desaturation. Okay, and so this is again in large part due to the ability to increase alveolar ventilation in relation to metabolic demands. In terms of the saturation of the blood, you can see actually that there's a subtle decrease during heavy intensity exercise, normally on the average of about 3 to 4% from rest. So in other words, if you're at rest and your percent saturation of blood through an oximeter is, let's say for example, 97%, which would be pretty typical, is that at the end of exercise, it wouldn't be uncommon for a healthy individual for their oxygen saturation to drop to 90, 94, 95%. So it would drop by about 3 or 4% from rest. Now this is not pathologic, this is actually physiologic, because remember the Bohr effect, right? The Bohr effect explains, what does the Bohr effect explain in terms of the oxyhemoglobin dissociation curve? So, put another way, exercise-induced increases in body temperature causes what type of shift to the oxyhemoglobin dissociation curve? So, commit to it. Down and to the right, up and to the left. Down and to the right. Exercise-induced changes in pH causes what shift in the oxyhemoglobin dissociation curve? Down and to the right. So the idea then is that at any given PO2, so in red, at any given arterial PO2, right, which is on the x-axis of that oxyhemoglobin dissociation curve, the rightward and downward shift of the O2 dissociation curve results in less affinity of hemoglobin for oxygen, which means that even though the arterial PO2 is preserved, that subtle shift is going to result in about a 3 to 4% reduction in oxygen saturation because of the decrease that the exercise-induced temperature and pH changes cause in terms of the affinity of hemoglobin for oxygen. And so this 3 to 4% reduction in saturation during heavy intensity exercise that it would exist in most of us is normal. Now, if you see a 10%, a 12%, a 15%, that's pathologic, and that's usually some indication of some severe ventilation perfusion abnormalities, either due to a cardiac disturbance or a pulmonary disturbance or some combination thereof. The point is that 3 to 4% is normal and can be explained by the Bohr effect, which is largely a temperature and pH-induced rightward-downward shift of the oxyhemoglobin dissociation curve. In terms of blood lactate, you've seen this before, is that blood lactate levels will remain relatively constant, which again, it's not that lactate's not being produced, it just is that the rate of lactate production, so basically appearance and disappearance, are being matched and is not appearing in the blood. Right? But then you get to a certain point during heavy intensity exercise, well, blood lactate levels will rise, and correspondingly, blood pH levels will fall. So you're developing this metabolic acidosis when you transition from moderate to heavy and peak intensity exercise. You can see this point here, somewhere about 50% of the exercise intensity, where we have this point which is the ventilatory or anaerobic threshold, the lactic acid threshold, the onset of blood lactate accumulation. I don't really care what you want to call it. It's a transition point where exercise demands become increasingly more intense, and it's usually, again, as we said before, that signpost that exercise cannot be sustained indefinitely. It's kind of that point where we move on to that very curvilinear portion of the power duration curve. Remember that? So you have the flat portion of the power duration curve where you can walk forever, but then you move up that curve, the more steep part of the curve where you're generating power outputs that can only be sustained for certain periods of time. And so generally when you're moving up that curve, you're definitely exercising above the ventilatory threshold. And it's at that point where you can see that ventilation increases disproportionately more than the rate of oxygen consumption. You're blowing off CO2. You're getting some acidosis and some desaturation, in large part because of, pretty dramatic increases in body temperature, as well as arterial blood acidosis. And you're also around this time getting a change in the breathing pattern. So generally, this ventilatory or anaerobic threshold occurs, depending on your level of fitness, within a range of about 50 to kind of 70% of somebody's peak or maximum VO2. The more fit you are, the higher the VO2 it will require. The less fit you are, it's going to occur at a lower VO2. Okay? So this is kind of the normal ventilation, breathing pattern, and blood gas, acid-base response to exercise. So, the ventilatory response to progressive exercise above and below the T-vent is worth highlighting. So, again, these are all the plots that I showed you before, just really taking out the breathing pattern response. So, if you look into this text box, minute ventilation and alveolar ventilation increase quite linearly with metabolic rate, or the rate of oxygen consumption, up to about 50 to 70% of somebody's VO2 max. Thereafter, ventilatory parameters increase disproportionately more than metabolic rate. So if you're bringing in more oxygen to the lung, and you're blowing off more carbon dioxide than's being produced, the inflow-outflow model, again, is going to dictate that you're going to rise your oxygen levels and you're going to decrease your body stores of carbon dioxide. Right? So it makes sense then that the alveolar PO2 levels will rise, even though in an attempt to maintain the arterial PO2 levels, right? So it's widening that driving pressure to facilitate the gas exchange in the setting of an increasingly hypoxic mixed venous PO2 that's returning to the lung that needs to be reoxygenated. So once it hits the arterial side, in the end of basically the transport through the lung, you can see that the arterial PO2 is preserved. You're also blowing off carbon dioxide, so you're increasing ventilation above and beyond that's technically required by metabolism, and so this is really the definition of hyperventilation. So hyperventilation is increasing ventilation disproportionately more than is required by metabolism, and the signpost of hyperventilation is a decrease in CO2 levels and a corresponding change in hydrogen ion. So, if you, right now at rest, if you increase your ventilation by 3-4 times, that's a true hyperventilation because you've forced yourself to breathe disproportionately more than your metabolic demands require. But if you increase your ventilation threefold in direct proportion to increases in metabolism, while you're hyperventilating relative to rest, it's not a true hyperventilation because you're not breathing in excess of metabolic demands. Okay? So, but during heavy intensity exercise above this kind of 50 to 75% point, the excess ventilation, so this alveolar hyperventilation, during exercise above the ventilatory threshold is related ultimately to the increased carbon dioxide, and this kind of should dovetail well with the acid-base lecture that came, and we'll reinforce it here, is that the increased carbon dioxide or the reduced pH produced during bicarbonate buffering of hydrogen ion, that's ultimately produced through the production of lactic acid. So lactic acid gets produced, it dissociates into a lactate ion and a hydrogen ion. That hydrogen ion needs to be buffered in a way to try to prevent severe acidosis. And so you have these bicarbonate ions that are going around kind of like Pac-Man, combining, creating carbonic acid to be transported back to the lung, then to ultimately be blown off. And so really this excess ventilation is occurring through this, in part through the carbon dioxide, as you'll see, that's being produced through the bicarbonate buffering of metabolic acidosis. It's not actually metabolically produced CO2. It's buffered CO2. Does that make sense from the last lecture? So carbon dioxide, so hydrogen ion is being produced as a result of increased glycolytic flux. as you'll see, maybe it's just best to go to the next slide. So yeah, it's just best to go next slide. So here we have the rate of carbon dioxide production, plasma lactate levels, and bicarbonate levels relative to exercise-induced increases in VO2, or exercise intensity. So you can see here at the anaerobic or ventilatory threshold, it demarcates a point where the rate of increase in carbon dioxide production, or the rate of carbon dioxide production measured at the mouth. Okay, so this can be both metabolic and non-metabolically produced, as you'll see. It begins to increase at a disproportionately greater rate than oxygen is being consumed. So now basically you're getting a greater flow of CO2 to the lung than oxygen is being consumed. And remember, we don't control ventilation in proportion to the rate of oxygen consumption. We control ventilation in proportion to the rate of carbon dioxide production. And you should be able to go back to the second pulmonary lecture and be able to appreciate why that is, going through those gas equations, why matching alveolar ventilation to VCO2 and not VO2 is so important, right? So at this point where VCO2 begins to rise disproportionately more than oxygen consumption, you can see that we get this rise in lactate levels and fall in bicarb. And so this is really because the standard amount of bicarb in the blood is now decreasing because it's going on and eliminating itself because it's now combining with hydrogen ion. So the bicarbonate ions are becoming carbonic acid ions, which means that these individual bicarbonate ions are decreasing in their concentration in the blood. So during intense exercise above the ventilatory, anaerobic, or lactic acid threshold, we know that lactic acid gets produced by an increased rate of glycolytic flux. So pyruvate gets produced at a faster rate than can be utilized by the mitochondria. Pyruvate has two fates. It either shuttles into the mitochondria or it turns into lactic acid, which then dissociates into a lactate and hydrogen ion. And then thus causing this metabolic or lactic acidosis. In the blood, bicarbonate combines with the hydrogen ion to form carbonic acid. So this is that buffering that I talked about at the end of last class, how like in many ways how CO2 is transported throughout the blood. In the lungs, so once this bicarbonate acid is produced kind of like in the blood at the muscles, in the lungs, this carbonic acid will dissociate to produce carbon dioxide and water. And so this dissociation, so you can imagine now that the blood returning to the lungs, this carbonic acid dissociates. So not only do you have the metabolically produced CO2 that's appearing back at the lung in the mixed venous blood, that's going to be expired, but now all of a sudden you have this carbonic acid, which is produced by the buffering, the bicarbonate buffering of the hydrogen ion, that itself is liberating CO2 molecules. And so now you have both metabolically and non-metabolically produced CO2, which is contributing to this widening disparity between the rate of CO2 appearance measured at the mouth versus the rate of oxygen consumption measured at the mouth. And so this increase in the slope of the VCO2-VO2 relationship during strenuous exercise is ultimately believed to reflect the excess CO2 that's produced by bicarbonate buffering of hydrogen ion, which is ultimately a byproduct of the lactic acidosis that comes from an increase in glycolytic flux. Okay. So, why is there a respiratory compensation for this acid-base balance? The respiratory system, again, has feedback loops that respond to disturbances. So right now it's colder than typical, and so for example you have a thermostat in your house, right? So if all of a sudden somebody opens the door and your temperature is set at 21 degrees. In the middle of summer, somebody opens the door, hot air rushes in, it senses an error, that error says it's now 25, turn on the air conditioner, and try to bring that temperature down by 4 degrees Celsius to reach this set point, okay? Same thing now, got it set at 21 degrees, nice and comfortable, maybe for some, it's comfortable for me. All of a sudden what you do is that you open up the door, it's minus 16 outside, cold air rushes in, thermostat says turn on the furnace, you get this feedback loop until the air is corrected and then the furnace will turn off. So in the respiratory system, we have these chemical sensitive sensors. We've got the carotid bodies at the base of the neck, that kind of taste the blood for hydrogen ion as well as other bloodborne factors and are sensitized by oxygen. And then we also have the central chemoreceptors, which are hydrogen ion sensitive receptors located throughout the brain, but with a high density in the medulla and the respiratory control center. Okay? So what happens is that when pyruvate gets produced at a greater rate than can be used by the TCA cycle of the mitochondria, we get this production of lactic acid, which generates this lactic acidosis. This lactic acid, again, will dissociate a lactate ion and a hydrogen ion. Now, it's hydrogen ion as is really what we're trying to prevent in terms of acid-base disturbances. Okay? So hydrogen ion then, ultimately, this increase in hydrogen ion will signal in a feedback-related manner. It will activate the chemoreceptors. And as you'll see, in particular, it seems to activate the carotid chemoreceptors. Some cool experiments where you do exercise below and above the ventilatory threshold in people with and without intact carotid bodies. And what happens is that during sub-ventilatory threshold exercise, surgical removal of the carotid bodies has no effect on the control of ventilation. During exercise above the ventilatory threshold, when there is acidosis, ventilation is significantly depressed relative to people with intact carotid bodies. So it's telling us that the carotid bodies are probably are operating in a feedback-related manner during heavy intensity exercise in the setting of a systemic acidosis. So this chemoreceptor activity will then signal a signal to the medullary respiratory control center, which will increase in a feedback-related manner alveolar ventilation. This will then serve to increase alveolar ventilation disproportionately more than the rate of carbon dioxide that's being produced metabolically. So now we have a circumstance where we're clearing from the lung more CO2 than is being delivered to the lung. The net effect then is that we're going to have a decrease in the alveolar and therefore the arterial CO2 levels. So go back to that normal response, heavy intensity exercise, they decrease in the setting of increasing acidosis in the body. And again, if you come back to the gas equations that I showed you previously, is that the reduction in arterial CO2 will serve to restrain the magnitude of rises in hydrogen ion, which in a feedback-related manner will try to correct the initial disturbance, which was acidosis. But at the same time, the reduction in arterial CO2 levels will serve to increase the alveolar PO2 levels, which is explaining why during heavy intensity exercise you're getting that increased amount of oxygen in the lung to facilitate gas exchange, or to facilitate oxygen exchange from the lungs to the increasingly hypoxic mixed venous blood. So again, this kind of ties feedback loops and all of the different equations and formulas that we showed kind of back together of why respiratory control system can operate by increasing alveolar ventilation disproportionately more than carbon dioxide production to compensate for the metabolic or lactic acidosis, restrain the rise in hydrogen ion. It doesn't prevent it, it just kind of restrains it, slows it down a little bit, but also facilitating or helping to preserve the oxygenation of the blood. Okay? So like that's a slide in particular where you might want to go through the animations and not just kind of look at it. So ventilation during exercise is largely controlled in many ways where we breathe to regulate hydrogen ion, and this is through the control of PCO2 levels. So you see this nicely here. This is Carlman Wasserman, kind of a godfather of clinical exercise physiology a few years ago, combined data that looked at the relationship between minute ventilation during exercise and arterial hydrogen ion levels and arterial CO2. And what you can see from this graph is that the ventilatory response to exercise and exercise-induced increases in acidosis, so arterial hydrogen ion, is pretty linear. So in relation to that last slide that I showed you, you can see that minute ventilation is increasing in large part due to this chemoreflex stimulus, which is the acidosis. Okay? And the way that it tries to prevent or restrain the magnitude of the rise in hydrogen ion is by controlling the amount of CO2 in the blood. And you can see that here, where ventilation is rising relatively linearly with increasing hydrogen ion levels. You can see that early in exercise, CO2 levels actually rise below the lactic acid threshold, but then they drop below resting levels during heavier intensity exercise. So again, we have this respiratory compensation for metabolic acidosis. We are eliminating CO2 as a means of trying to prevent the rise in hydrogen ion, which is ultimately contributing to the stimulation of ventilation during exercise. So the take home here is that in humans, arterial blood hydrogen ion is regulated in large part through the ventilatory elimination of carbon dioxide from the mixed venous blood during progressive exercise, and this is particularly true at intensities above the lactic acidosis threshold or the ventilatory or anaerobic threshold. In other words, we breathe disproportionately more than metabolic demands, we blow off CO2 as a means of trying to restrain the magnitude of rise in hydrogen ion, which would cause a very severe and rapid acidosis, which we know has negative consequences on cell function and to some extent the rate of development of muscle fatigue. So we need to have a fast-acting physiological support system to try to minimize that effect, and the lungs just happen to be that. The kidney operates way too slow. It's hours and days to regulate acid-base balance. The lungs are very rapid based on the extent to which you ventilate. So, this is a bit of a gnarly slide, but it's important because it has big implications. If anybody of you looked at the lab handout, this lab is actually really cool, by the way. It's this first year that we did it. I did the experiment yesterday of breathing through a dead space and wearing the weighted vest and all this type of stuff. And I mean, walking at 5% grade at 4 miles an hour is really not all that tough. But when you're wearing a 50-pound vest and you're breathing through half a liter of dead space, it's pretty gnarly. So for like me, the dead space alone increased my ventilation, I think, by 10 liters a minute, and then when I added the weight vest to the dead space, it went up by like 35 liters a minute. So the whole idea of the lab is really to take what I'm going to show you on the next two slides and like show it to you visually. We think we have enough time to do 4 people per lab, which means that we'll have 12 participants to average the data, which should show pretty nice graphs and help you answer the questions. If you actually look at the lab handout, the questions that are coming are directly related to the implications of excess weight and metabolism, say related to obesity, and then added physiologic dead space to, say, COPD as a lung condition, and then what happens if you have comorbid obesity and high dead space due to, say, emphysema. And so I've given you a bunch of articles that drive that, several of which me and my colleagues have published. But the idea here is that you can look at the individual effects of exercise-induced increases in metabolism, added effects of metabolism, added effects of dead space, and then effects of body mass loading, and then their combination. So the idea here is that it should kind of show you a lot of these variables independently and then combined that we'll talk about now. Okay. So the ventilatory demands, ventilatory response to exercise depends in large part on 3 physiological factors. So metabolic requirements, particularly the rate of production of carbon dioxide, the dead space to tidal volume ratio, so what percentage of each breath do we need to ventilate, kind of like the dead space in our respiratory system, so those non-diffusible portions of the lung and, say, poorly ventilated or perfused areas of the lung due to pulmonary blood flow issues or ventilation issues. And then also the regulated level of CO2. So we all have kind of like a CO2 set point. Our body is set to try to regulate carbon dioxide levels, and most of us between 36 and 40 millimeters of mercury. And that exists basically anywhere across the world, across people. So regardless of age, sex, height, gender differences, geographical differences, we're all generally regulating CO2 levels somewhere between 36 and 40 if we're healthy, normal people. Okay? So the ventilation is equal to this constant value, don't worry too much about it, multiplied by the rate of carbon dioxide production, divided by the regulated CO2 level, multiplied by 1 minus the dead space to tidal volume ratio. So what this formula indicates is that ventilate at any given PCO2 and at any given dead space to tidal volume ratio, ventilation will increase if metabolism increases. At any given metabolic demand, ventilation will rise. At any given metabolic demand and dead space ventilation will rise if PCO2 levels need to be regulated lower. It also says that at any given metabolic demand and any given regulated level of PCO2, ventilation will be higher in the setting of increased VDVT ratios. The opposite of all those factors are true. Ventilation will come down at any given PCO2 level in any given dead space if you have less metabolic demand. If you have a more homogeneous lung with less dead space at a given metabolic demand and a given level of CO2, you don't have to ventilate as much. Okay? So that's the formula, and then this kind of gnarly graph describes the interrelationships between these factors. So what I'm showing you here is that this is minute ventilation on all of these y-axes. Okay? This is the minute ventilation at VDVT ratios of 0 and 0.8. Okay? So basically what you're getting is you get progressively worsening ventilation perfusion ratios. So this is a perfectly ventilated and perfused lung with absolutely no dead space. 100% of the breath does not have any dead space, which is not physiological. Okay? And then you can see is that you're rising. So 15% of your tidal breath and then 80% of your tidal breath is basically wasted. Down here on the x-axis we have the arterial CO2 set point or equilibrium point, and then what we have here are what they call these isoplests. Okay? These isoplests describe, so we have is these various carbon dioxide levels. So what these isoplests describe is the relationship between VCO2, so at any given VCO2, the relationship between arterial CO2, minute ventilation, and dead space ventilation. So I'll break this down iteratively. So, for example, a ventilation that is high for a given VCO2 during exercise, i.e. an increased VE-VCO2 ratio or slope during exercise, can reflect an elevated dead space to tidal volume ratio. So some type of ventilation perfusion mismatch. So let's say, for example, in this case, an increase in the dead space to tidal volume ratio from 0.2 to 0.5. So in this case here, we're going from 0.2 to 0.5. Okay? At a VCO2, a rate of carbon dioxide production of 2.5 liters a minute. So now we're tracking along this isopleth at 2.5 liters a minute, and an arterial CO2 level of 40 millimeters of mercury. So now at this exact CO2 level. Okay? So what we're showing is that at this CO2 level and at this rate of carbon dioxide production, going from a dead space of 0.2 results in a minute ventilation of about 75 liters a minute. But increasing the dead space ventilation to maintain that same VCO2, to support that same VCO2 and support that same regulated level of carbon dioxide, will now result in a ventilation of nearly 120 liters a minute. So you're getting nearly a 45 to 50 liter a minute increase in ventilation to support the same arterial CO2 and to support the same rate of metabolic demand when you have an exaggerated dead space. So this is basically a ventilatory compensation for wasted, inefficient lung. You have to ventilate more to compensate for the level of inefficiency to support a given metabolic demand. So for example, walking up a flight of stairs at a given amount of arterial CO2 in your blood. Okay? Alternatively, let's say for example that you had a reduction in the arterial CO2 equilibrium point, which will occur with, say for example, a respiratory alkalosis. So this actually occurs in human pregnancy. Pregnant women going from the follicular to the luteal phase of their menstrual cycle, and then if they actually get pregnant, going from that high hormone phase of the menstrual cycle into early pregnancy, will have a rise in ventilation that will blow off CO2, which actually causes a respiratory alkalosis. It creates a gas exchange gradient between the fetus and the mother. So the mother becomes alkalotic so that the baby can actually develop in a normal pH environment, and it creates a pH buffer so that the baby can develop basically with some protection against intrauterine acidosis. So the mother will hyperventilate, kind of, again, whether or not this is creation or evolution, I don't know, it's not what we're talking about here, but the idea is a pretty cool system. So pregnancy, for example, is a situation where there is a respiratory alkalosis, which means that a pregnant woman, for example, has to regulate her CO2 levels in the setting of exercise at a lower level than when she's not pregnant. Typically on the order of 8 to 10 millimeters of mercury. So it could go from 40 to 30, right? So this is kind of the example that we're giving now. And so take, for example, now a reduction of arterial regulated CO2 levels from 40 to 30 at a VCO2 of 3 liters a minute, and now an unchanging dead space of 0.2. So now if you have at a PCO2 of 40 and at 3 liters a minute, this will result in a ventilation at this VDVT ratio of about 85 liters a minute. If you then force the respiratory system to regulate CO2 levels at 10 millimeters of mercury lower, while supporting the exact same metabolic demand and the same level of VDVT, or the same level of wasted ventilation per breath, you can see that the ventilation level now has to rise by about 20 to 25 liters a minute. So the idea here is that an increase in ventilation relative to metabolic demand can be caused by an increase or wasted ventilation, so a high dead space to tidal volume ratio, which can occur in cardiac and pulmonary diseases, or circumstances where you have to regulate the CO2 levels at lower values. Okay? So if you look at this a slightly other way, if you look at the VE-VCO2 ratio, which will vary in proportion to the PCO2 set point in the dead space ventilation, you can see it this way. So the VE-VCO2 ratio, in this case, the VE-VCO2 ratio at an arterial CO2 level of 40 millimeters of mercury, changing or worsening the dead space from 20% to 50% will result in almost a doubling of the ventilatory requirement to support a given metabolic demand. So when you think of VCO2, this would be like your body mass walking up 3 flights of stairs. Okay? So to maintain your arterial blood CO2 levels at 40 millimeters of mercury and walking up 3 flights of stairs, which will have a fixed metabolic requirement, the ventilatory response would be twice as high if you had 20% of every breath were wasted versus 50% of every breath were wasted. So you can see the consequences of, say, having ventilation or perfusion issues due to cardiac disease or pulmonary disease. It forces you to breathe a considerable amount to support a given level of ventilation. This is often occurring in these conditions where the room to breathe is actually deteriorating. So you have this dramatic drive to breathe, but you have less room to do it. The net effect is people become incredibly short of breath, doing almost negligible physical activity. Right? This is like taking a cylinder out of your car, but asking it to drive twice as fast. Just can't accommodate. The car's going to blow up. It's kind of the symptomatic manifestation of these pathophysiological abnormalities that occur in cardiac and pulmonary disorders, where they have an exaggerated requirement to breathe, but they physically can't do it because of either obstruction or restriction of the lungs. The alternative is that at a given dead space level, so in this case at 50%, so 50% of every tidal breath is basically wasted, you're going to have, again, a higher VE-VCO2 ratio if you have to regulate your CO2 levels at a lower value. So again, perfectly normal, healthy pregnant woman with no change in her dead space ventilation, no change in metabolic requirements, will require more ventilation to support her metabolic demands because she now has to regulate ventilation at a lower level to accommodate the baby. So there is a ventilatory stimulation of pregnancy that seems to be, as one example, important. This would also occur in a compensated metabolic acidosis that could occur, like diabetic ketoacidosis or something like that. Okay, but the point is that you're getting an appreciation for the factors that can contribute to ventilation. Metabolic demand, dead space ventilation, regulated level of CO2. Generally speaking, even in disease, the regulated level of CO2 is pretty well preserved. So you rarely have hyperventilation or hypoventilation syndromes. So the primary factor that would be contributing to an exaggerated ventilatory response is most often an elevated dead space to tidal volume ratio. But we'll talk more about that in exercise path next semester. All right, so That's how we breathe. So that's kind of like the stimulus to breathe. Now we need to consider how we breathe. So we come back to pressure-volume relationships. So, did I show you this? I showed you a spirogram before. I think I did. You had the responsibility of knowing lung volumes and flow volume loops, spirograms, and the pressure volume curve, right? I think that's what I tasked you with. Yeah? Okay. So, this is a spirogram. Just hypothetical, but this is really largely what happens during exercise. So again, here, just to anchor your orientation. Big breath into your lungs are full, total lung capacity. Blow all the way out to your lungs are completely empty. From your lungs are full to your empty, that's your vital capacity. That's the biggest breath, that's the biggest, I have a slur on it, that's the biggest breath that you can take, okay? Of course, we have a little bit of residual volume of air that we can't access because of collapse of the airways during expiration. And then we go to normal breathing. So we breathe in, we breathe out. We breathe in, we breathe out. The lung volume at the end of a normal breath in is aptly named the end inspiratory lung volume. The lung volume at the end of a normal breath out is the end expiratory lung volume. The difference between the end inspiratory and end expiratory lung volume is our tidal volume. That's the tidal breath. We have the difference between total lung capacity and end inspiratory lung volume is our inspiratory reserve volume, the volume within which we have to expand inspiration. And we have the expiratory reserve volume, the volume that we have to expand expiration. Okay? So we have these reserve capacities. On a flow volume loop, if you remember, that would be the loop in the middle. We have the expiratory and inspiratory reserve volumes to the left and to the right. Okay? So, at the onset of exercise, what happens is that tidal volume will begin to expand in a healthy individual. And this occurs by actually decreasing the end expiratory lung volume from its resting value. So with active recruitment of the expiratory pump muscles, we actually will increase intra-abdominal pressures, flatten out the diaphragm, and decrease end expiratory lung volume, which will cause a recruitment of the inspiratory capacity. So you can see here that the inspiratory capacity during exercise actually goes up because the end expiratory lung volume